Hello, welcome back to the today class. Today we will talk about the proximity queries. So these are the class objectives. I wish that we can at the end of this class lecture material you can understand the collision detection, also distance computation, which are the very common two of these proximity queries. And then basically to perform this kind of the operation, we usually use this bounding volume hierarchy. And then at the end of this talk, we will talk about how we can actually use the point cloud that are commonly used when you're using the sensors. The details about this material will be covered in the chapter 5 of my book. Also, last time we talked about this C-space. We talked about what are the actual homotopy classes, also some other issues related to the C-space. So so far we talked about lots of things, but these are the two main geometry primitives that we are commonly used for in the C-space. One is the clear at a particular configuration Q. This means that at that particular configuration Q, whether we have the collision or not. So basically, if we don't here I'm showing this visibility graph. Here, so far this kind of node, right? So basically, at that case, we don't have any collision, right? So when you perform the clear operator at this particular location Q, then we don't have any collision. In other words, it's true for this clear operations. And then link between two configuration Q and Q dot. Basically, is check that whether along the straight line path between Q and Q prime in the C space, whether that along that line we don't have any collision or not. For example, from here to there, here actually we can think about this kind of the straight line path in the C space, and we don't have any collision, right? So at that case, if we call the link here to there, we will get the true. So basically, based on these operators, we can actually know in what locations we don't have any collision, also in what is line segments we don't have any collision. So based on that, we can generate node, also the edges in the graph. Then basically based on that graph, we know what are the actual connectivity of this C-free space in the C space. Then we can wander this motion planning, path planning. And then basically in the end, we need to have a very efficient mechanism for performing this clear and link operators. So the main problem saying for those operators is that there could be the two objects. Typically, one of them may be the robot, or the other one is the obstacle in the environment. And then output is that for the case of distance computations, we need to compute the distance, maybe they're in the workspace between A and B. Basically, the A and B is a robot and obstacle. So typically, the distance we typically use that distance in the workspace instead of the distance in the C space. But depending on your application, we may also use the distance in the C space. But commonly, we use the distance in the C space for the case of this distance computation between two objects like the robot, also this obstacle. Another one is collision detection. At that case, we need to check whether these two objects we don't have any collision or not. So basically, here when you have these two objects, the distance computation is that somehow we compute these 2 points where that give us the minimum distance between two objects. Also, the collision detection, basically there can be one people can treat that collision detection. To perform collision detection, we just run this distance computation, and then compute the minimum distance, turn out to the 0. Then we know that basically we will have collision, right? Also, we can but instead of taking this approach, there are actually dedicated technique for performing collision detection. Also, there are many ways of using this collision detection. Also, this distance computations. But here I'd like to talk about this issue. Typically, when you suppose that here we need to see that along this straight line segment we have the collision or not. In other words, we want to perform the link operator between these two configurations. One can just use the collision detection, right? But common collision detection is the kind of the discrete collision detection. It means that basically we need to generate we actually discretize this line segment as a set of these point samples here. And then along these point samples, we check the collision at that case, at that case, at that case, and so on. So basically, this is known as discrete collision detection. Basically, we run this kind of we perform these discrete collision detections along under these discrete samples, and we don't have any collision. We can treat them along this line. We don't have collision, right? Obviously, this approach has the issues, right? For example, even though we don't have any collision here under these discrete samples, they may be very small object along on here, right? And we may not miss collision, right? So that's one of the issue of discrete collision detection. But unfortunately, this discrete collision detection has basically proposed long time ago. Also, that has been used a lot. Mainly because that the simplicity, also we can perform this discrete collision detection in a very fast manner. So that's why it has been used a lot, and a lot of cases, most of motion planner techniques using this kind of discrete collision detection. But you should aware of that. There could be this kind of issues of missing the collision detection. But another one is that we can also use this distance computation to check whether this line segment has a collision free or not. Here, suppose that we have this line, and then basically at that point, this 2 point, and then along this line segment, we wanted to check whether it will be the collision free path or not. Here, we first check at that point, we check this minimum distance between this point from this configuration and this environment, and then basically we can know that this actually gives labor from the environment to that point, right? And then we can actually this will be the minimum distance, right? And then it means that if we generate this kind of ball that has the radius of this minimum distance, we know that in that ball we don't have any collision, right? We do the same thing here. At that configuration, we compute the minimum distance. This point this will give this minimum distance, and we know that on that ball we don't have any collision, right? And then we check that at that configuration, we check that these configurations are within this ball or not. In this case, actually these balls are disjoint, right? So we don't get any information. So then we recursively perform this operator by computing this middle point out of these two end point. And then here we check that we do the same thing. We got this kind of empty ball, and then we check that whether these points are within here or not. Nothing there. Then we check this middle point, and then we also do the minimum distance, and then we compute the ball. At that case, here at that point we got this kind of the ball, right? And then we check at that case these configurations actually are within this ball of this at that point, and then these points are within this empty ball associated with that point. Then it means that along the path from here to there without any collision, right? We can actually guarantee that without any collision. Then we can actually safely we can guarantee that there's no collision under this line segment. We can keep doing it actually, and we can guarantee that we don't have any collision along this path. Obviously, this will guarantee this actually has a much more accuracy compared to the discrete collision detection, right? But usually performing this operator actually turn out to be more expensive than this prior using the discrete collision detection. So commonly we are using a lot. But I wish that as we get a more faster computer with a higher performance capability, we can use this kind of operator. This is actually pseudocode. If you follow this one, this is just the pseudocode of what I've talked about here actually. And this kind of collision detection or also distance computation has been studied a lot, mainly because those operators, this proximity, the query, used a lot in various related applications like robotics for avoiding collision or path planning. Also graphics, virtual environment, simulation, common use them. Also haptics here. Haptics is that basically you might see this kind of device. When you control this kind of device, you can feel the force. This haptic device that generates force. And then to do that, you need to perform the collision detection, also the collision detection between your hand, also this virtual object, also compute this distance, right? then based on the distance collision detection, you can generate force proportional to that distance. So basically, in this application, collision detection and distance computation is one of the main ingredients. Actually, there are also many other applications. Also, before I talked about the discrete collision detection, also there are another technique known as continuous collision detection, which which guarantee that we don't miss any collision. So before, suppose that at the time step I-1, basically here we used collision detection along the trajectory. At this time step, we don't have a collision, right? And then discrete collision detection instead we simulate. In other words, we actually advance time, and then here at the next time we move the ball here, right? And then we check the collision over there. Then we see that there's collision, right? But here actually when the ball is actually moving very fast, at that time step we don't have any collision, right? And then we do simulate here, and then basically when you simulate, we don't consider this collision detection. And then at this time, we also check the collision, right? But we don't have any collision, right? Then we keep simulating at that way. Then you can see that actually we missed this kind of we missed the collision between this ball and this wall, right? Basically, to avoid this one, we usually use very small time step for the simulation, right? Then if you're using the small time step, then it takes a lot of time to simulate, right? So there are some of issues like this, and then also this is one of the issues of this discrete collision detection. As a result, there are actually continuous collision detection technique has been proposed. Its main idea is that you consider this continuous motion of this ball or under the object, and then under that continuous motion, we check that collision between that object having that continuous motion against this environment. So basically, considering the continuous motion require much more difficult operations, even actually solving some of the very complicated equation. But if you're doing the continuous collision detection, we can actually check what's the actual first time of contact and in what location we can have collision, which is very useful. Also, they're very useful for the design, very accurate simulation. But it comes with this very high this computation cost. But anyway, there has been the study on the continuous collision detection and discrete collision detection. Obviously, discrete collision detection it's kind of fast, but it may miss collision. On the other hand, CCD, continuous collision detection, is accurate, doesn't miss collision, but it can be slow. So, but whatever technique you are using, I would say that in most of the motion planning technique use this discrete collision detection. But when you are seeing the very accurate simulation, then at that case, continuous collision detection may be used. But whatever technique you are using, those techniques typically accelerate by using the bounding volume hierarchy. Let me explain the concept of bounding volume hierarchy. First of all, I'd like to talk about bounding volume. So for example, here we need to check the collision between this object and that object, right? But I assume that we might use the many triangles for representing robot also this environment, right? So basically, in a very live setting, checking the collision detection is that we go over every single pair of this triangle, that triangle, and see that whether we have collision or not. Also, we check the distance between the one triangle or another triangle here, and then we go over all the pairs, and then we take the minimum distance for computing the minimum distance computation, which is very slow, right? So instead of that, you need to have some sort of hierarchical approach using this kind of bounding volume hierarchy, but also we typically use this kind of bounding volume. For example, here we have certain object, right? And then suppose that here I have this kind of object, then I need to check the collision, whether I have collision between this object, that object, right? You can go through this triangle level, this pairwise triangle level between this object, that object, which takes a lot of time. Instead of that, we can typically using the bounding volume like sphere. For example, in this object, if we compute the sphere, the bounding basically sphere is the smallest sphere that enclosing this object. In this case, we can actually compute this kind of the sphere bounding volume. The main reason why we are using sphere is it's relatively cheap to compute, and then once we compute this sphere, then suppose that we are actually instead of checking the low level task between the triangle level 1, we check the collision between this object or this sphere. And then to do that, for example, we actually measure the distance between this object or the center of this sphere. And then the distance is bigger than this radius, we know that there's no collision, right? So basically, we don't need to go over the low level triangle level test. Also, for this object, we can also use another bounding volume, right? So that way we can accelerate this collision detection process. So in other words, that's why it's a cheap test. But it also has an issue. It can be potentially very bad fit. In other words, we use sphere, but actually it's kind of very conservative bounding volume, right? So here, at that case, say that this object located there, we know that between this object and that object we don't have any collision, right? But somehow this bounding volume is very loosely fit. When you check the collision between this sphere and this object as collision, right? Then we need to once we have collision between bounding volume object, then we need to refine the bounding volume with the triangle, and then we need to check this pairwise test between this triangle set, that triangle set, right? Then obviously we actually waste our time to checking to using the bounding volume test between this bounding volume and that object, right? So the better way is that we want to have the very simple sphere that can be a simple bounding volume that is actually the simple shape of bounding volume, so such that we can do the very efficient bounding volume and bounding volume test. And then also this bounding volume should be very tightly fit, so that actually we don't have this kind of one. And if we know that if there's actually so that actually we can actually very efficiently efficient representation for the collision detection. So typically instead of the sphere, one can actually use this axis aligned bounding box. You can see that it's more tightly fit, right? Also, the computing this bounding axis aligned bounding box is also very easy. Cheap test, also tighter than sphere in most of the cases. Since actually, if you look around our object, a lot of these man-made objects actually have this kind of axis aligned, this kind of regular shape. Also, there's another advancement on the bounding volume. One can use this orient bounding box. So given this object, it's not this kind of axis aligned one, not but here actually we even compute this orientation and compute this kind of more tightly fit one, right? But computing this orient bounding box require more computation than the axis aligned bounding box, even though it is actually tightly fit object. There are many other advanced ones like these KDOPs that using the very multiple actually this kind of planes. But typically the sphere and axis aligned bounding box or also this orient bounding box commonly used. Here we can accelerate this collision detection process by using bounding volume, but again we can also using this kind of bounding volume in a hierarchical way. So that's why we actually have a concept of bounding volume hierarchy, BVH. So organize bounding volumes recursively as a tree. For example, suppose that we have this triangle. Initially, we compute this kind of bounding box, right? And then here, we treat it as a root of the bounding volume hierarchy. And then somehow we partition these two triangles into the left and the right node. The common way of partitioning the triangle is that we actually we break this bounding volume along these longest edges. In this case, we break the bounding at that way, right? And then we actually partition the triangle, this triangle against that plane. A plane or line. In this case, this triangle goes to the left, this triangle goes to the right. And then there we also compute another bounding volume out of this one triangle. Then we can get the more tighter bounding volume, and then we treat that as the left and the right node, right? And then at one time, once we build this kind of bounding volume hierarchy, and then when at one time for checking the collision detection, first we do the collision checking by traversing this hierarchy. At the first time, we check between this object or the root bounding volume. If there's no collision between this bounding volume and there we stop it. We stop the traversal. It means we don't have any collision. But if we have the collision here between this bounding volume and that object, we'll refine this bounding into two children bounding volume here and there. And then we check that here we don't have collision. Here we have collision, right? Then between this bounding volume and that one, then we refine it. And then since this is a leaf node, then we only have the triangle. Then we check triangle. We check the collision between this triangle and that object, right? that way we traverse the triangle. That way we can actually checking this collision detection. This actually when you have the two objects, right? One object, another object, and then we can build the bounding volume hierarchy that object or another bounding volume of that object, right? And this is general case. Then we actually start with we checking the bounding volume between these two nodes. If there's collision, we refine it. Then we need to check the collision checking here to there, or here to there, here to there, and here to there. We need to check all the pairs between bounding volume. And then some of bounding volumes without any collision, some bounding volume we have collision, right? So for that here we have collision, right? Then we actually we stop the traversing, refining this node, that node. Here we have collision, we refine that. So then we need basically these two triangles associated with this node, triangle 5 and 6 associated with this one. Then out of there we look at all the pairs and then we check the collision between these two, between the triangle here and there. This is actually general setting of the collision detection out of these two objects using these two different bounding volume hierarchy. Basically, this bounding volume hierarchy is actually concept very simple, and basically this concept is very widely used for collision detection. But actually, a long time ago, we actually work on the ray tracing, which is actually used a lot for the rendering in the field of computer graphics. Ray tracing is nothing but we actually generate ray, and then we need to check whether we have collision along that ray and this environment. And then basically somehow back then the people didn't use bounding volume hierarchy for ray tracing, but we knew that we can use bounding volume hierarchy for the ray tracing. Especially works. I didn't talk about actually how we can. I briefly touched on how we can build the bounding volume hierarchy. Also, we can very efficiently build the bounding volume hierarchy for the even dynamic scenes. Dynamic object like the moving robot. Also, here actually we apply this technique for this kind of the dancing character with a very long skirt. It is very small image, but actually basically for representing this skirt, this is nothing but dynamic object. We need to update the bounding volume hierarchy every frame. But somehow we felt that we felt the bounding volume hierarchy. Using bounding volume hierarchy for handling the dynamic objects, actually, it was actually very common practice in the field of collision detection. But somehow we found that the ray tracing community didn't use the bounding volume hierarchy. And then back then, actually, handling the dynamic objects for the ray tracing becomes one of the most important topics. So to us, actually, it's very it was a very easy choice for using the bounding volume hierarchy for handling ray tracing of the dynamic object. So, but somehow we didn't really see that how it actually how it will be contributed, what kind of the contribution it will make in the field. But somehow 10 years later we got this test of time award. Basically, it means that somehow this technique actually turned out to be very useful within even though 10 years passed. But here I'd like to point out that basically some of the concept may be very common to you, but applying the concept to the related field, then basically that may make the very big contributions. If somehow if you can make some of the link between these two different fields. Okay. Also, so far I talked about using the bounding volume hierarchy for the collision detection. But same technique can be used for even the computing distance. So here also we can use the bounding volume hierarchy. Also we can do the traversal on the tree. Let me show you this simple example. Here actually we want to compute the distance, right? So initially we don't know the what distance. Here actually I want to compute the distance between this point also this object, right? Initially we don't know the distance, right? So initialize the distance as infinite. So we set initial distance value to infinite, and then we traverse, and so far we build the bounding volume hierarchy using the sphere on this object. And at that case, we measure the distance between this point and this sphere. Then the distance 20. 20 is smaller than infinity, right? Then we refine two nodes, and then we pick this one, since this gives us the most smaller distance to this point. And then here we got the distance of 40, smaller than infinity. We traverse deeper. and then here, now actually we traverse, we choose this node, and then actually this turns to a leaf node. So actually we measure the distance between this point and that point, and then we got the 42. Now this actual distance, right? That coming from the triangle. So we this 42 is smaller than infinity. So actually we already found the minimum distance at 42. I mean this is actually our current candidate for the minimum distance. As we traverse more, we might be able to find the triangle that gives us more smaller distance, right? But anyway, based on this one, we actually set our initial we update our initial distance as 42. Then we keep traversing, and then back then we didn't refine this one, and then actually we check this one. At that case, actually the distance between this point and this sphere is the 45. Do we need to refine this node, or we can just skip this one? Basically, the distance between this point and bounding point is 45, right? And then it means that if we refine this node further, and if we touch the leaf node triangle within this bounding volume, obviously the distance between that triangle, that point should be bigger than 45, right? Since actually this sphere is the kind of sphere is actually the kind of this tighter bound, right? So that means that even though we can traverse there, but if we traverse there, the minimum distance should from those triangle may be bigger than 45. But our current minimum distance is 42. Then we don't need to traverse more there, right? Since there's no hope that we can refine, we can actually update, we can actually minimize the current distance. So we skip this one and we traverse other node, and so on. So basically that way, based on this one, we can actually skip the traversing particular node. Also, we can actually, some people say that we can cull, or that we can prune the traversing from this node, right? That way we can accelerate the runtime process of computing the minimum distance out of the bounding volume hierarchy. And then again, let me talk about the time complexity of building this tree or bounding volume hierarchy. If we assume the roughly balanced the binary tree bounding volume hierarchy, then basically when you assume the n triangle, then the height of the triangle should be the log n, right? And then at each node, we traverse the older triangle, the n different triangle, and we partition them, those triangles into left and right node, right? Every level, we need to do that, right? So here, there will be n triangle, we partition them. There will be also the n triangle at the level, and we keep doing that, right? They are actually log n height. So that's why basically the time complexity of building the tree is typically the expected times n log n. Also, the tree can be built once, and then basically if we assume that the steady environment actually, if we assume this steady environment, then we can keep using this bounding volume hierarchy. Also, there are even though the environment is moving, there's technique that we can very efficiently update the build the bounding volume hierarchy. But how about the traversing the tree, the runtime cost of performing collision detection, or also this minimum distance computation? At worst case, actually, there might be no culling, right? At that case, we need to traverse all the nodes, right? Then you can very easily see that there are n triangle. Basically, there could be also the big O of n nodes, right? So at worst case, actually, the full search require big O of n traversal time. And also, in addition to that, also we need to spend some time for computing distance between a point to each triangle in the model, right? Actually, but this is actually the worst case analysis. But in most of cases, they might be culling, right? So typically, also the best case is that we just traversing only the one branch of the tree, something like here. We just traversing one branch here. We travel here, and then we just terminate, something like that. And at that cases, the time complexity of running the collision detection or distance computation turn out to the log n plus the sum of the low-level collision detection test between the triangle and some other one. But actually, usually this runtime cost vary a lot depending on these geometric shapes. For example, this one object is another object, if these two objects actually align very closely, we might have to do the full search. But if the objects are very located very far away, then this might be we just traverse one branch might be enough, then log n. So typically depending on the geometric configuration between two objects, in worst case log the big of n or the log n. Also the bad or some of the cases actually we might have the log n, and typical learning time happens between them. So if I talked about actually this kind of proximity coverage mainly with the triangle, but if you're using the sensor data, a lot of sensors actually provide this kind of point cloud. So there are a lot of recent technique actually basically they propose to handle this kind of point cloud in an efficient way. So let me just briefly play this video. Here, actually the robot comes with this Kinect sensor RGBD here, and then we got the depth sensor, and then somehow we got the point cloud, and then we build this kind of grid representation, 3D grid representation. The red cell indicate that there are the probability that we have obstacles, something like that. So it's very common to get the point cloud like this depth image, and then we somehow represent them into this kind of obstacle map represent in the grid or some other representation. So when you are using the sensor data, we typically we get a lot of point cloud, but this actually the point cloud is a very irregular representation, and there could be many points. So directly using point cloud may not be efficient. So somehow we represent them point cloud into the manageable data structure like the sum of the map, the grid or the arctree, something like that. And then on top of that kind of representation, we do the actual path-planning some other applications. We can just use the 3D grid map, also this kind of arctree and some other representation. Yeah, I'd like to talk about occupants map representation, which is very commonly used for handling the sensor data. Which main idea is that somehow we are using this kind of grid map representation. We can use simple 2D grid, 3D grid, or grid. Also, we can use arctree. But anyway, and then basically in each cell here, we wanted to encode the occupant's probability. It means that what are the probability to have the obstacle at that particular location. And then here, I'm not going to talk about all the low-level details of mathematical derivation. Also, we are using the sensor while we are actually moving around the scene, right? So in other words, at t-1 time, we already collected the sensor information. We already updated. We already had this map representation, right? And then at the next time step, we got the new sensor data, and then we somehow incremental updated the existing map information by using the current observations. So I'm not giving you the exact definition of what this L function means, but it means that we actually collect the data along the time sequence, and we somehow accumulate it. And then one common method is that suppose that here actually we have one point cloud, and this is sensor origin. Then it means that we actually from here to there we don't have any collision, right? But we at that cell contain that point. It means that there's a probability that we have certain obstacle there, right? And then by working, then we actually walk through here. We don't have any collision. We have collision, right? And based on that, we update certain value. Basically, this value is actually it's not really important to understand what this value means. But basically, higher value means that there's higher probability to have collision, something like that. And but we found out that actually when you actually have the very good sensor, there could be many points even in the one cell. There are four different. We might have the 4 different points even in the one cell, and then we need to actually this process from the sensor origin and every single point by walking through this cell, and also we have to update this value, and obviously it takes a lot of time, right? So actually, back then we also proposed that. Actually, instead of traversing every single from here to there, we actually identified a set of those points where we can actually have the exactly same traversal pattern in terms of this in terms of the traversal pattern from the sensor origin to each individual point, and then we actually group them. We call it actually super array, and then we just traversing only one time. That way, actually, we can improve this updating updating time of the map. That way, we can very efficiently update the sensor data, have this map representation, and do some other operations like collision detection. Also, there could be also learning approach. For example, the learning approach is that we might have the sensor data here, right? Here, the one point, another point, but in between, you don't have any information, right? But depending on your application, we want to know that whether whether we have the obstacle or not there, right? And then basically even though we don't have any sensor information over there, we can somehow look at around the nearby information, and actually and then we can estimate whether we have collision or not at the locations. Also, recently we work on the learning-based approach to have that kind of the environment information, even though we don't have the exact sensor information. But I'm not going to talk about all the low-level details, but actually there are lots of things going on. If you're interested, I recommend you to go over this paper, where also I showed this link, and then there could be many other related techniques. But anyway, I hope that you can understand the collision detection and distance computations are very commonly used for many applications, including motion planning, and we commonly use the bounding volume hierarchy. Also, recently to handle sensor data provide a lot of point cloud, and then we can use some sort of more simple representation like the grid of the octree. You can treat the octree as a kind of type of bounding volume hierarchy, and then based on that, actually based on that information, we can do the other collision detections. Okay, that's it. Next time I talk about the probabilistic roadmap. And again, same thing. You need to submit the summary of the two papers before the Tuesday class. Go over the next lecture slide, and then you need to come up with these questions before the midterm exam. Yeah, that's it. Thanks so much. Bye.